In this demonstration, we examine the foundational pathway of utilizing the MYRTUS DPE, Design and Programming Environment. Building a TOSCA model in TOSCA Designer is the first step in the DPE workflow. Here we have opened the TOSCA Designer project for the MYRTUS mobility use case. Topology composition is done by first defining node types. Then we define node templates and establish relationships, for instance to specify in which compute node the software components will run. Let's take a look at one concrete node template for the mobility use case. For the sensor tracker node template, we have metadata properties for the Onyx spec file and the TensorFlow Lite spec. We set the values for these properties here below in the TOSCA properties view. These values are later used in the step 3 of the DPE flow. Then, we can define explicit constraints, such as budget constraint or latency objective within the model. This prepares the model for design time optimization by external tools like Frevo and Cosmos, enabling swarm intelligence algorithms to determine the most optimal deployment blueprint prior to orchestration. Furthermore, before generating the deployable artifact, the designer facilitates the modeling of attack-defense trees to reason about security countermeasures, which in the demonstrated example includes encryption-decryption and key exchange mechanisms. We are now ready to export the CSAR file, the Cloud Service Archive, which is the file format we use for exchange in the DPE. For this, we right-click on the root of the TOSCA model, we click on Export, and we generate the file. Here is the TOSCA file, with all the node templates and properties we have just defined. A full hands-on tutorial for the TOSCA Designer is readily available for review on the official YouTube channel. We will now see the hardware optimization step.
For mobility use case, the TOSCA file specifies the paths of the model to be compiled, such as this tiny one on the right-hand side. Thanks to the YAML specification of TOSCA standard, we can read this path easily as reading the YAML file. Then we can import this model using array importer to MLAR. Then we can apply custom Python methods to read out layers information which will be used in the next pass to generate the code for step 3. In step 3, we apply convert to emit HLS pass pipeline to get the code before translation. Such as here, we have memory and stream interaction. We apply the sliding window optimization, and we maintain the same compute kernel as the input. In the top function, we insert pragmas for memory interface, streams, and data flow optimization. Then we can use the translate tool to generate C++ file to use in VT's HLS. We also generate a few very useful scripts such as this one, the Python library to instantiate accelerator using the generated hardware, as well as the scripts to automate the hardware generation process. I will now show you an example. After specifying 2 environmental variables, we can run the automated script. Now I will jump to the result. The generated hardware will be copied into deploy folder. Now I will show you an example on the board. On the board, we will use the generated Python library to instantiate the accelerator. We also implement a software version to run on CPU. As a result, we achieved more than 150 speedup.
The MCC toolchain starts from the model just shown, now expressed in the QNX format quantized with QKeras. With this command, we can run QNX on DC, generating inputs for VT's HLS and the multi-data flow composer tool. In the output folder of QNX on DC, we find cal files for MDC, C++ files for VT's HLS, and a folder to hold synthesis results. Here is a convolutional layer template filled with the parameters extracted from the QNX model. A Taco script can then run automatically VT's HLS synthesis. From the MDC frontend, we can inspect the network topology and then run the accelerator generation. By running the MDC scripts on Vivado, we will produce this block design from which we can generate the FPGA B-stream. If you are curious and want to see more, the QNX on DC repo includes a step-by-step tutorial for building an adaptive CNN for MIST.